As we discussed at the end of last chapter, now we want that we've understood the place of the sciences and what philosophy is and what modern science is. I want to go through and do what's probably been in the back of your mind for a long time, seeing how this squares with all the things that we know in modern science. We can't do all of them, but I thought I'd bring up some of the ones that I've seen in the last, in the 20 years that I've been a scientist, that have caused the most confusion. Even in some cases, confusion that leads to people to doubt man's very capacity to know, and even the existence of the world itself. These 6 areas are 5 bullets here, but 2 of the areas are under relativity, and that's backward and forward time travel. We'll discuss forward time travel, and we'll leave backward time travel to the book. It's more complicated. Inertia, the Big Bang Theory, we'll discuss, and evolution. Quantum mechanics we'll leave to the book. It is itself a whole lecture. This Bell's theorem is a theorem that is basically an ontological theorem that some have called the most important discovery of science. And I give in here the first detailed proof that this is not true ontologically. So I encourage you to read that section, especially if you have interest in the science of physics, because this is a key thing in physics. And you will hear people talking about it and discussed in books you might read. But it'll also help you understand how these errors come about in modern thinking. So let's start with inertia. Inertia is the tendency of a body to continue in its state of rest or uniform motion unless acted on by an outside force. Everyone's heard that in their basic physics courses. But what does inertia mean to most people? Well, to the average person in science, inertia means that motion doesn't need a cause. To them it appears that one man's motion is another man's rest. They often imply that rest and motion are just 2 states of being that are not really different, just relative. Totally relative, in other words. They may go further and argue that inertia disproves Aristotle's ideas. This is triply wrong, as we can see by now, with our background and understanding, building up the base slowly of our knowledge. And basically the ontological identification of rest and motion as all being is at bottom the error of Parmenides, saying that there is no change. So it's an old error. There's nothing new under the sun in that sense. Another way to look at it is if you were to say that motion is staying at rest, you could say that it's the error of Heraclitus. I said everything is change. The other thing we can note is that the specialized cannot overturn the foundational. The foundational is used by the specialized. It cannot overturn it. One is using the empiriometric mode of explanation also as directly ontological. We saw that that's an erroneous thing to do as well. To unwind and see the philosophy at work and see how to look at these things, we'll start with inertia and we'll move naturally forward in the progression of the science of physics, and we'll end with an example from biology, which is the evolution example. And to do this, we'll first uncover the history of inertia, and this whole issue of improper knowledge versus proper knowledge will come back to the fore as we talk about the influence of the culture and which things in the culture are giving us good improper knowledge that when tested give the gold of proper knowledge. And this, in particular case here, we'll be looking at one aspect of the culture that's so important to having this respect for the non-necessary character of the world. Inertia is the first really successful principle of physics beyond the fundamental principles that we've enunciated so far. It was first a real principle. Now we're talking about physica, the full science of physics, the study of changeable being, not just as mathematical. Now it's mostly an empiriometric concept. And this is where the error came from of this identification of motion and rest with inertia, because it was interpreting an empiriometric concept as ontological. So we're going to start with where it is now, thought of as purely empiriometric concept, and move to the ontological by way of history. Now, the empiriometric system of Newtonian mechanics has 2 pieces, the energy and the linear momentum. The linear momentum has a direction associated with it. And basically linear momentum is that the tendency of the object when thrown to keep going in its direction that was set in. Now, if you just said, well, let's have just energy conservation alone, then what would happen? Well, it would not guarantee that the object continued in its given direction, because you can conserve energy, it turns out. The equation for energy, if you may remember, is 1/2 mv squared, kinetic energy. And so it can conserve that kinetic energy if it's, say, going down a north-south road, heading north down that north-south road. It could veer off into the grass and conserve energy. By the same token, if there were only energy conservation, when one pool ball hit another pool ball, there would be no law by which they split that tendency. Now this and the Newtonian mechanics that go with it, mathematics of the Newtonian mechanics that go with it, explain how it happens, but not, what happens, not how it happens. The imperial metric, again, is not ontological. We have to make that step, and we should make it deliberately. What will happen if you don't make it deliberately is you'll make it in a confused, incoherent manner. So we want causes. We have to move to analyzing this philosophically. Fundamentally is basically all we mean when we say philosophically. Back to the first principles. What is motion? Motion is a process of the reducing of something, a patient, from potentiality to act by means of some agent. For example, water. So here we see a case of potentiality reduced to act, and that is water being broken down into its components of hydrogen and oxygen. And here you can see the hydrogen, I'm pointing here to the hydrogen and the oxygen now, which is half as much, because there's twice as much H2 as there is O2 in the water. And now we'll see what happens if you heat up the hydrogen. I've switched the tubes, and we'll turn off the light, and we'll put a little heat, and what we'll see is the hydrogen will combine with the oxygen has the potentiality of becoming water, and it does under the action of heat. So we see the potentiality being reduced to actuality. So motion is the process of reducing something from potentiality to act by means of some agent. In the case of the hydrogen, the agent was the heat. And the heat acting on the hydrogen and oxygen, we created water. And we can also talk about if I pick up a baseball and I throw the baseball across the room, the baseball is acted on by me. But the ball is here, it ends up over there. It's actually here and potentially over there. The ball is not everywhere at once, it's somewhere and potentially somewhere else, in the same way that the water molecules are actually hydrogen and oxygen, and only potentially, the constituents of the water molecules are actually hydrogen and oxygen gas, and they become water. They're potentially water, and they become water under the action of the agent, which is the heat. So how does, in the case of the baseball, how does something that is somewhere get somewhere else? Something else, an agent, moves it. Such an agent is called, as we saw, an efficient cause. That's all well and good, except for one thing. When you let go of the ball, it keeps moving. I'm an agent that acts on the ball, but the ball keeps moving. It keeps having action reduced, potentiality reduced to act, even though I'm not touching it. Very odd. Let's pick up the history now. Aristotle confronted this problem. This is after the foundations now know. We've established the foundations of the Physica, and even broader areas than that. But we've established the foundations. We're not talking about the foundations. We're talking about building on the foundation. Aristotle said, well, it's the air. The air is pushing it, going in behind it and pushing it. Aristotle confronts the problem of planetary motion, the fact that planets move, and says there are special separated intelligence for each one of them. Why these answers? After all, they tend to contradict his own dictum of starting from the senses. They're pretty far from the senses. Medieval commentators refuted them pretty easily by examples, as we'll see. They moved beyond the data very quickly and missed the commonality of these two problems, the motion of the planets and the motion of a projectile. Well, we come back to the importance of the cultural milieu. Aristotle's principles don't lead where he went. There must be other influences at work, and indeed there are. The pagan influence to eternalism, which we see over and over again in non-Catholic cultures or non-Catholic seeded cultures. And Stanley Yaki has documented this very well in several of his books. He calls it the Great Year. And it basically boils down to some having to do with the necessity of the world, the eternalness of the world having a necessity of itself, that is the reason for that these other cultures were not fertile places for science. And we'll discuss this more, but if you think the world is necessary, then you have a tendency to do what happened in classical times, pre-Christian times, which is to think that you can just go into a room and figure out the world. You don't have to look at it, because it's necessary after all. You should be able to figure it out a priori. So we found even Aristotle, his genius and his understanding was not enough to fend off the improper knowledge that his culture radiated to him, these strong cultural influences, because his principles themselves do not lead him necessarily to those conclusions. So we will not be surprised that the first real criticism comes from the Catholic culture soon after the Catholic culture has had a chance to take over, and that comes from John Philoponus of Alexandria. And Yaki says, Aristotle's theory of motion did not lack critics, but none of them was as incisive as in Philoponus. Philoponus hit right to the heart of the matter. He said that the Creator could make the sun and the moon and the stars be given a certain kinetic force in the same way as light and heavy things were given their trend to move. And he goes further and says that, and generalizes this as saying that, this same force that the Creator given to things could be the reason that they continue to move, as well as the reason that the planets continue to move. So this all comes from the Christian understanding of the freedom of God and the unity of creation, these two things, because the other influence from the pagan culture was that the world is divided into these separate places that don't necessarily fit together. Aristotle was completely against this notion, but yet he was in a culture that believed these things and so influenced by them in subtle ways. Again, the importance of searching your proper knowledge and checking as often as you can those principles. But the fact is the freedom of God made these people realize that the world didn't have to be the way it is. It is the way it is because of a free choice from God. Therefore, it obviously did not have its necessity. Aristotle also demonstrated this in principle, but St. Thomas was to bring this out with clarity and leaving no room for an educated mind to go astray on it again. But in an atmosphere of improper knowledge based on these beliefs, you can see why Aristotle would go astray. Indeed, you wonder at his ability to go as far as he did, given the background. Now, this was all rediscovered after the barbarian invasions, when Europe again came to some stability, and there was the first universities in the world were founded. And John Buridan refutes this notion by a very incisive example. He talks about a mill wheel. He says, a great mill wheel moving around will not slow down just because you try to fan the air away. Because if you take a rag and wipe the air away from the wheel, you will not stop the wheel in this way. If the air which I set in motion when I throw a stone can move the stone, why will it be that if I blow the air as swiftly as you can at the rock, that the rock doesn't move? Easily refuted by these people. Aristotle's dictum that the air was what moving it. Therefore, the mover impresses on the moved thing not only motion, but along with it a certain impetus, or some force or other quality, not the kind of force we usually mean by the name, which impetus has the nature of moving that thing on which it is impressed, just as a magnet impresses on iron a certain force moving the iron to the magnet. And the more swift the motion, the more intense the impetus will be. And this impetus in a rock or arrow is continually diminished by the resistance of the air. In a place before this, Buridan argues that the mill wheel would continue forever if there were no resistance. This is the principle of inertia enunciated in the Middle Ages, long before Newton. He goes on to say, it would not be necessary to postulate separated intelligences to move the planets. The planets would run by inertia, or as he called it, impetus. This is the early 1300s, and Buridan is already saying that this impetus is proportional to the mass and the speed. This is momentum, linear momentum. Granted, linear momentum without detailed analysis and experiments and equations, but again, this is the early 1300s. This is 200 years before Galileo. This is one of the giants that Galileo stood on, one of the many. This is basically comes from the work of Pierre Duhem. As I mentioned, 10 volumes where he discovered to his shock these things that had been left out, and still are, by the way, left out of most history books. But you can find them if you look in the right places. It's just that it's a matter of slighting rather than denial. St. Thomas gives the first distinction between, St. Thomas himself contributes to the science of mechanics by making the first ever distinction between mass, weight, and resistance. And there's others, Brodredine and Grosseteste and Orsum and on, people that contributed to these. Let's go back now and see if we can understand this empiriometric theory and looking at the ontology underneath it and see what's going on underneath it. So as a research hypothesis, we might say, we have to include the broader areas of physics and try to understand the ontological causes, the real being that's causing what we see. Well, momentum, we will say then, is a measure of this quality of impetus that is given to an object when it is thrown, for example, or when one object hits another object. And that's the tendency of the object to move in a given direction. It's a mere accident, meaning that it's not belonging to the essence of the thing, except from the fact that the thing has the ability to have that. For example, this thing has the ability to be at different temperatures, but that's not the essence of the apple to be at some particular temperature. It can be, at room temperature. It can be the temperature of your fridge. Mere accident. So this is a mere accident of again, it has to inhere in another, but it's not part of the essence. Mass then will be the measure of the resistance to this action of this impetus. The more mass, the less fast it will move in response to a given amount of impetus. Energy then becomes a measure of another intensity that I call the dynamis quality, the ability of the object to move generically. And for example, this dynamis quality can be converted to heat. So some of this in a collision that's so-called elastic collision, some of like two pool balls, most of it stays in kinetic energy. Most of it stays in the dynamis, the quality, the kinetic dynamis, I should say, and which then appears as an impetus, on a certain impetus on each ball. But sometimes if the balls are like gooey or something, they might a little bit stick together and heat's created. So some dynamis is converted to you might want to call caloric dynamis. But basically it's to random motion as opposed to particular motion. So this sort of very quick analysis, which has to be true at least at some general level, to avoids the absurd conclusion that motion and rest are the same, and respects nonetheless the empiriometric conclusions that you can't question either, because they are coming from the observed realm, although in an obscure manner that you can't directly interpret. You have to analyze as we did. This brings us to consider time and space. Relativity and quantum mechanics are empiriometric theories. And in one way they set free the empiriometric. But in another way, they caused a problem because they were not clear about the fact that they were empiriometric. They set free the empiriometric because they stopped requiring within the empiriometric to be properly physica, to be properly philosophically. So they let the tool become what it is, and that is formally mathematical. In the past, they sometimes would try to sneak ontology into the metric, into their measurements. They would try to sneak it in here, so they would really radically confuse the nature of this tool, which is to be formally mathematical and materially physical. But on the other hand, not thinking that this was all of reality, and not making the distinction between what the thing is and this empiriometric organization of the thing, an empiriometric quantitative understanding of the thing, if you will, you get all these kinds of false notions that we'll discuss. For one of them we've already seen is this problem with inertia. Special relativity then will come on and combine space and time and acts as if space and time are the same thing. And to understand, let's talk about relativity of motion, which brings us back to inertia and kind of through the back door. If we can understand relativity of motion, then it will be on our way towards understanding how these confusions happen in the case of Newtonian physics. Galileo and St. Thomas before him recognized, many will not know this, recognized the relativity of perception of motion. They commented on it. Nonetheless, it's called Galilean. This type of relativity of motion is called Galilean because of Galileo's really insightful experiments that he did showing this. And in some ways, though, he really just quoted Orsim, and some of these people came before him. He used and he depended on, used that improper knowledge that he got from those other people and verified it himself and then extended it. Ironically, Newton, in trying to preserve physica, was not clear about its imperiological, ontological distinction that need to be made. He tried to be clear, but he kept sneaking it in the back door. And one of the things that he did, he made motion, time, and space absolute in the sense that they exist independent of bodies. And we'll see that that is absurd, ontologically speaking. It's fine empiriometrically. It's a fine thing to do empiriometrically. We found we did it already with the plot of time, distance versus time. Remember that? That was basically, we said, putting space and time on the same level, basically, as spatial variables, which they are not. But you can do that empiriometrically as long as you're conscious of it, that you're doing it. So we cannot take pure relativity of motion as an ontological reality. But many do from a long empiriometric habit of thinking about these things. Let's analyze the question of relative motion. Motion, again, is the process of reduction of potentiality to act. I have the baseball, it's here, it's potentially over there, I throw it, and the impetus causes it to move from here to there, where it potentially is to where it actually is at the next moment. Now, take two identical pool balls, and let's assume they're shooting away from each other like this. B will, and now if you're on A, and B will either appear to be stationary, or it'll be moving if you're sitting on A looking back at B. Well, in our case, since they're moving apart, you look back at B, and B is moving away from you. If they're moving, how do we decide which one's moving? Because all we have in our universe now is two balls, A and B. A is going this way according to B and A in the other direction according to A. The empiriometric scientist would say it makes no difference. If you're on A, it looks one way. If you're on B, it looks the other way. That's all there is. But we know differently because nothing can change itself. Remember the principle of causality? Nothing acts except as it is in act. Nothing can change itself. One ball is moving or both are moving. We need to decide what the split is. Local motion, remember, means change of place. What is place? It's one of the categories that we saw of material things. It is a body's relation with respect to the surrounding bodies. So the place of this is so and so distant from all these things with the air molecules around it and so on. Back to our two identical balls. If only two balls and no media, if this is possible, and it isn't, but let's just assume this because it makes it easier to think about, then the only motion possible is relative motion between each of them. Because after all, place is nothing but your relative position with respect to the surrounding bodies. And there's only one other body, and that's the other ball. Which is being moved toward the other? Well, it depends on which is being acted on. That is, which has the impetus. Because remember, one patient and agent. So there's an agent that's reducing the patient, which is actually somewhere, to where it can become somewhere else. So the impetus is what's doing that. So we can use what's called in physics the center of mass concept, which is an empiriometric concept that we're trying to understand ontologically, and we're doing it at a very loose level just to get you to understand how that there is an interpretation that needs to go on to understand the causes behind things. And that if you do this carefully, that's a lot of work, but it saves you from saying dumb things in the end. As you'll see, there are really some crazy things being said when this is not done. And the way you can do this is say, let's extrapolate back when these balls that are flying apart would be at some place at the beginning. In that place, there would be no way of saying the thing is moving, because there's no other balls. When they're together and stop, there's no other, they're stopped, they have to be stopped because there's no other balls to refer to. So, and from the center, if you use this imperiometric concept of center of mass and you can properly interpret it ontologically this way, then you have to say that they both have the same amount of impetus going in the opposite directions, and they're both being acted on then in the same way. So this is one way of understanding how the balls behave. But this is not really possible because we're not we haven't been talking about what's possible for a rational animal, because an animal, remember, is in the material world. He has to see things through his sensorial knowledge. That's man. Man is a rational animal. He has to see things through his sensorial knowledge. How is he going to see what ball B is doing when he's on A? There must be signal being sent from one to the other. Light must be bouncing from one to the other. Our view is what I call the view of Maritain angel, a view of an immaterial being, a being that can see things without having to use his sensorial knowledge, can see sort of what's happening here and there just by moving there instantaneously. We cannot do that. And this is an analogy, by the way, to Maxwell's demon, the famous and justly so physicist James Clerk Maxwell, the founder of the theory that we now use for light, had discussed thermodynamics, and in so doing he invented the thing called Maxwell's demon, which is basically a demon that he hypothesized doing certain things, and he would in a thought experiment what this would mean. So in our experiment we were basically using what I call, after the great physicist, great philosopher Jacques Maritain, Maritain's angel. We were using his view of things. To really do it right, we have to include light, because there has to be some way of signaling so we can see what that other ball is doing. And this leads us straight to special relativity. And this is actually not very different than the way Einstein came to special relativity. Now, special relativity is more imperiometric than Newtonian theory in this sense, that it takes literally this relativity of motion and the mixing of space-time. It acts as if time is really just only slightly differently than space. I mean, is actually only a slightly different thing than space. And it takes literally the relativity of motion, which we saw you can't do. So it's more imperiometric in that sense. Remember, this is fine as long as you remember what it is and what its limits are. It's less imperiometric because, unlike Newton, Einstein considered how you'd actually have to do the measurement and realized that there had to be something like light. Not an angel eye view. This allowed him more correlation of phenomena. Newton never asked the question how to correlate times. Now again, we're talking imperiometric. He didn't do this ontologically, he did this imperiometrically. How to correlate times. So if you want to picture yourself what they're talking about here, put yourself on a train, on the back of a train, say in the caboose, and here's the tracks, say, and there's a clock next to the tracks, and it's sending out beeps with the time encoded in each beep at regular intervals, say second intervals. Now as you pull away, as the train pulls away, you look at that clock. Well, when you're sitting still, the clock is separated by 1 second. It agrees with your watch, and the time agrees with your watch. But as you pull away, it takes longer for that next beep to get to you. So your watch shows more time going by, and it looks like time is slowing down for the people on the ground. Now as you go faster and faster and faster, that effect accumulates. And it looks like time is slowing down. As a matter of fact, if you keep speeding up, if you speed up fast past the speed of sound, you will catch pulses emitted before you left. Time will appear to go backwards. So imperiometric time can slow down, speed up, even go backwards. But notice it's imperiometric time. It's the correlation of one measurement with another measurement. This is key. So we must consider how things transmit their actions to one another. And that's what made Einstein more ontological, because time and space are dependent on material things. If you take away all material things, then you have no time and no space. Because time, we'll see, is the measure of motion, and space is what you get when you abstract everything away but quantity. So anyway, this is immediately viewed in such a way that it can be mathematically expressed. That the quantitative unity of the measure can be manifest in beings of reason. In so doing, mixing up the time and the space in a being of reason, it becomes an ontological soup with all kinds of different things, the actual things causing the particular things in an equation. To sort this out, let's look at special relativity and one of the things that you probably heard about, the so-called twin paradox, and talk about forward time travel, that is going forward in time. In this paradox, we won't discuss the paradox aspect of it so much, but just the fact of the time travel. In this paradox, there's two twins. And the one twin is a stay-at-home twin, and one twin wants to go to this planet in the Andromeda constellation, the star Upsilon, which is about 50 light years away, meaning it takes 50 years going at the speed of light to get there. And it has these planets that are named B, C, and D. This is really their names, by the way. And by the way, planets, having seen planets outside of those in our solar system is a fairly recent thing in the last 10 years. But let's say one of the twin wants to go there, and one of them wants to stay home. Well, special relativity, in the imperiometric theory, which imperiometric theory are correlations of measurements, and that includes their predictive ability, how well they can correlate those measurements so they accurately underlie the quantitative interrelations, including over time, that take place. If you go at 0.806 the speed of light, this c means the speed of light, it will take the travel twin 20 years by his reckoning. This is what the theory predicts. Remember, the theory is good at predicting. We're going to trust the theory for its metric predictions, not for what it means, but for what the measurements will say. By the stay-at-home twin, we'll see 102 years. So the stay-at-home twin might be dead by the time he gets back, and his brother will only be 20 years older. So what do we make of this? Well, the imperiometric explanation will tend to use highly mechanistic explanations. It'll be something that's consonant with the mathematics. It's easy to understand in terms, there's a bunch of equations that we don't need to bother ourselves with that it will try to explain. It will leave out the other categories. Remember, there's 9 categories. It will leave out quality, relation, action, receptivity in favor of quantity. Special relativity gives equal value to all reference frames. So we can pick out one frame and just say, this is my favorite frame. I'll do things from here. And we can interpret relativity in the most obvious way and say that time really does slow down. How can this happen? Well, we need to know what time is to answer that question. What is time? Time is the measure of motion. It's numbered motion. And you measure, so basically things that repeat are the standard by which you measure motion. And the more fundamental motions control the other motions. And motion, remember, is only possible because we're form-matter composites. Material things are form-matter composites. If there were no material things, there would be no reduction of potentiality to act. So without material things, there is no time. St. Augustine recognized this very early in in other places this was not recognized, again for the same cultural reasons we mentioned. Thus, absolute time that Newton defined, time existing of itself, makes no sense. So back to our twins, now that we know what time is. Let's assume that our stay-at-home twin rests with respect to this global frame that we've chosen, so that he's not moving, and there's a bunch of other things around him. Well, let's not assume that. Let's just say that anybody that wants to go near him and stay at rest with respect to him will be in this frame. Less time passes for him and his buddies than for the travel twin. He can have less breaths. He can play less games of chess, has less conversations. Less things happen for him. That's what it means. Time is the measure of motion. But note again that each bodies are regulated by the bodies in contact with them, by their place. And a really good way of seeing this is when the sun sets. The sun is controlling a lot of the things, of the timing of the things on the earth. Most things in the timing of the earth, actually. When the sun sets, it triggers winds. It triggers nocturnal activity of animals. People turn on lights. All kinds of things are triggered by the sun setting. And another way to see this is in a smaller scale is like if you take an embryo and you freeze it. Basically what you've done is you've kept outside contact from influencing it. The outside contact can no longer regulate the embryo, and it stops, basically, quote unquote, stops the embryo's time for the embryo. Time freezes for the embryo, if you will. It doesn't freeze, it just goes really slow. So we can see already that you can slow time down because time is just the measure of motion. If you make the contact such that the motion slows down, the time slows down. Another example is if I go outside, I get cold. The outside environment impacts on me and it starts to cool me down. So let's look at the twin paradox in more detail. And by the way, this should be 20 years in both directions, summing both directions, not one direction. Let's say that each twin is equipped with a watch that emits powerful beams of light once a second. So every time my clock ticks 1 second, it emits this powerful beam of light that can be seen at arbitrary distance. So the travel twin on his own watch will see 20 years worth of pulses for the whole trip. That amounts to 7,300 pulses. The stay-at-home twin, I call him ST, on his own watch will see 37,000 pulses, 102 years worth of pulses. Stay-at-home looking at the travel twin's watch is, for the first half of the trip, sees 3650 during the first phase, which lasts 101 years for the stay-at-home. In the last year, however, he will see also 3650, giving a total of 7,300 pulses that come from the travel twin's watch. Now, by contrast, the travel twin looking at the stay-at-home twin's watch sees 365 during the first phase when he gets to the planet, which for the travel twin lasts 10 years, and 3,800 during the second phase, which lasts also 10 years. This is very odd asymmetry between the two things. How do we explain this? Somehow a different pace has been set for the travel twin relative to the stay-at-home twin. What causes this? By assumption, there are no other bodies. It cannot be the planet itself. It cannot be Earth because Earth shares that same time slowing that the stay-at-home twin has. And it cannot be the spaceship for the same reason. We're at a point that often happens in modern physics, and that happens in physics, as you see now, where we can't explain within the system that we've put ourselves something that we're seeing happening. In modern physics and empiriometric physics, what you do at that point is you introduce another being of reason to explain the phenomena and incorporate that being of reason into the already existing theory. In this case, we're going to postulate a new real being. And that real being is a non-mechanical ether. It is a body, but in our sense, in our extended sense of philosophy, not what they talked about in the 19th century, a mechanical ether. It does not need to have mass or any of these other properties. It just needs to be a form-matter composite. Such an ether is at rest with respect to the Earth, say, our global frame. So things moving with respect to it will interact differently with it than things at rest in it. So what we could say is its activity sets the pace for all things. Those things that are at rest with respect to it will couple better to it and will have faster flow, more motion, faster time. Those that are moving relative to it will have less coupling and therefore less time. We can postulate this as a way of showing you that we always have to look for these causes underneath the empiriometric explanations because they are begging for the ontological to explain them. And one example is the electric field travels in such a way through this medium so that the laws of special relativity are satisfied. So this is what is the sort of effect that the ether is like in the Big Bang Theory. In the Big Bang Theory, you have an expanding, and this expanding is actually what's causing the changes that you see, driving the changes that you see. In the Big Bang Theory, at the beginning, the Big Bang is hot and dense, and as it cools down, as it expands, it cools down, and you get the first atoms forming. First you get hydrogen forming to helium, then you get stars, atoms forming, and then stars forming. And from the stars you get heavier elements forming. And this is all driven by the expansion of the universe. So that by this ether, if you will. So this naturally leads us to general relativity, which we could talk about next, but we won't because there's not time. But in the book it's talked about. And let's stick to special relativity because the ideas are what's important here. How you look at these theories is what we're trying to get at. And what kind of work needs to be done to understand them without confusion. Special relativity then is very beautiful when viewed in its proper context, empiriometric context. And we haven't even touched the beauty of that theory. Because to do that you'd have to be putting mathematics up here. When one wants the real that is responsible for measured quantitative aspects manifested by the equation, one needs physica. That's the lesson to take away. Such rethinking doesn't usually affect back on the empiriometric, but it may. You may decide that this leads you, for example, as it did just now in thinking about the larger ether, may lead you to thinking about general relativity or something like that, and lead you to the next empiriometric theory, next empiriometric triumph. Physical theory, physica at least in the narrow sense, has been responsible for lots of new empiriometric discoveries, which then pave the way for ontological understanding, if you keep in mind the limits. What will happen if you're not careful, though, is that you'll say time and space are interchangeable or can be mixed up into each other, which they aren't because we know what time is. Time is a measure of motion. Space is that abstraction that you get by taking away all motion. In short, the hidden problem with the xt plot mentioned before will come home to roost as a full-blown hypothesis. When we drew xt before, we said, look, somebody might think that we're saying time and space are the same thing. Indeed, that's exactly what happens when people look at special relativity without the proper view of building from the base up. Time and space in empiriometric relativity are both quantities distinguished only as different by having different quantities associated with them. So we said the difference between time and space ontologically is clear, and we have to be mindful of that. And when we can understand these theories for what they are, we must be just cognizant of what we've left behind and what beings of reason we've introduced. Beings of reason, again, are things that cannot exist outside the mind. We must be conscious of our limits of our minds. We're not angels. We do not have innate ideas. Our ideas are abstracted. Hence, angels don't need the empiriometric because they can get things directly. We have to go via tools and beings of reason to get lots of our understanding. But don't be confused. Don't let the tool, don't let the hammer that you're going to build the house with, don't get so enamored with the hammer that you forget that the purpose of a hammer is to make a house. After all, physics in the wide sense of physica is about finding truth of material things, of conforming our minds to that particular reality. So another danger that happens very often is in these empiriometric theories is brought out very clearly by Kant. Again, Kant is the icon of these things because he came up with a very nice philosophy that describes this empiriometric world to a T. And it comes up with all the problems you have when you think of the empiriometric world as the whole world. He asks, is there a universe? Kant actually brought into the question the very idea of a universe as being crazy. And of course, a universe is a horrible thing to waste. And Einstein, by empiriometric thinking, again was able to bring the universe back into respectability as if it should have ever gone out of respectability. How did he do that? By empiriometrically including time and space, and thereby inadvertently bringing back the fact that time and space are parts of the universe, not something that exists independently of it. And I recommend here Stanley Yackey's book, There Is a Universe, where he philosophically goes in and shows where these errors are in more detail than I'm going to do here. The universe that we need to define, the universe is all things taken together considered in their unity. It's a universe. Uni meaning one, verse meaning turn, one world. So this brings us to the Big Bang hypothesis, which Einstein was instrumental in coming up with because this theory of relativity, which I just mentioned, general relativity, brought the universe back into respectability by sneaking it in through the empiriometric. And basically, we've described the beginnings of the Big Bang hypothesis. And the Big Bang theory says that the universe was very hot and small and gradually cooled down and got protons and atoms, as I said, and then stars, and from there, different elements. It predicts the universe began 15 billion years ago, and that at that point, there's a mathematical singularity. Empiriometric science on the face of it seems to say that the universe began right at that point, came into existence right at that point. Is this proof the universe came from nothing? No. If one means by creation what you should mean, which is ex nihilo, from nothing. This is not a proof in the strict philosophical sense. We'll see it's an indication, not a proof. The universe is. Remember, the degree something is the degree that it is one, that it has unity. So all the parts of the universe are related to each other. It is a multitude of bodies, it's sort of a republic of natures that all interact with each other, and to the degree that they form a relation among each other and they have this unity is the degree that it is. And within this universe, forms are lost and adduced. I eat an apple, the form of the apple is lost, and it becomes part of the form of me. An animal dies, a form of an animal is lost, and the form of the carcass, the substances that make up the carcasses are adduced, brought forth. But the matter is preserved during all these changes. Even the death of an animal is not the absolute loss of an animal, because the animal still is potentially present in the carcass. It can in principle be made, as we saw. The material is there, and the laws, if you will want to speak empiriometrically, but better said, the final causes ordaining the act towards potentiality and the potentiality towards act remain. This potentiality cannot be destroyed. We've seen this. You can do whatever you want to the thing. You can put out whatever form, and there's something underneath that we call matter that is preserved. Matter is neither destroyed or created during these processes. And it's based on understanding its own nature. Understanding the nature of the universe, one cannot prove the universe has a beginning or end. One can have indications of this, but not proof. A singularity in a mathematical equation is a singularity in a mathematical equation. It cannot tell you about something coming into existence. As far as you look at it, this matter does not change. It is preserved underneath all changes, and so you have no reason to say at any particular point that can go away, just of its own nature at least. So by studying that nature, you're not going to be able to come up with a proof of it. But the Big Bang does give a pointer towards that. And we have to remember, again, the limits of the empiriometric to say ontological things. We're going to see this even more clearly now as we move to evolution. Evolution is usually limited to the study of life in an empirioschematic approach. I'm going to include the material evolution and give a whole picture. But the empirioschematic approach in life, again, results because the empiriometric, the mathematical, is much harder and does not work as well because of the fact that once you get to the biological, once you get to the higher levels of life, the first accident is really very complicatedly hidden by all the other accidents that are more largely present. Remember, the more something is, the more complicated it is, the more that those relations obtain and the more unity there is. So there's more than just mere quantity there. There never is just mere quantity, but as you get closer to the sort of constituents of things, you get closer to the quantitative, and physics then, the imperial metric then works better. So it will tend to build beings of reason in a world parallel to the real world, not the ontological. So it'll build up, as we said, with putting all the insects with a certain number of legs in one category. It'll tend to build up these categories and then try to look back and see what it can say imperial schematically about them, and then come up with new categories if it has to. The problem of understanding the underlying real being responsible for the order manifested in these schema then is our problem. Like the imperial schematic and the imperial metric, it will be interested in purely material causality. Why? Because it wants predictability. It wants repeatability. The imperial schematic will also take many samples so that it can take an average to get some stable answer. And thus, it'll be in general a mix of various effects from various real beings, and an average of those kind of effects. So you don't want to identify too closely with a schema as being a particular individual thing in the real world, because it's really the result of, in 99% of the cases, of the action of many different material things acting. Now, any immaterial effects will be implicitly included in the schema, but not recognized, because we're trying for predictability in these schema. And immaterial things, basically things, we've seen that materiality is associated with knowledge, and purely immateriality is associated with intellectual knowledge and a will. And so a will mean that you cannot predict what it's going to do. It can do whatever it decides to do. And so we will deliberately want to exclude these in our imperial metric scheme, but they'll pop up because they're there. So, but we'll keep adding beings of reasons to explain the phenomena in the best possible way we can. How can the imperiological approach then include everything? And that is, how will it incorporate the immaterial things that are there, that have no extension and must not be readily amenable to mathematization? Because remember, extension is nothing else but the quantity, the first accident of material things. And these are immaterial things. They have no quantity extension. How can they be classified in these material models? It cannot. The real question is not how is it going to be incorporated, but how will it appear since you haven't incorporated it? It will appear as randomness. Chance is a mechanism that can and should be used both in the imperial metric and the imperial schematic scheme. Anything radically different than the schema will appear as a sort of irrationality in the system. Chance is nothing else, is really irrationality within that system, meaning no reason within that system. So we'll come back to this issue of chance, but let's go through evolution and as it appears imperial-metrically and schematically, and assume that scientists have done their job correctly in this regard. So if we said first that the universe is this hot ball 15 billion years ago, it gradually cools down. The quarks form into protons. The protons then form into atoms. Then the atoms coalesce into stars and galaxies. And finally, at some point, we have a solar system develop with planets around it. And then one of those planets, Earth, say, among the rocks and water and gas in the atmosphere, the first simplest forms of proteins appeared, and then the simplest life. Eventually developed into animals and plants of all types. Philosophical terms here is what I'm saying. Finally, a man emerged. Some things survived, others, such as dinosaurs, did not. Each phase, notice, something different, more complex emerged. First a rock, then a plant, just an organism with nutritive powers, and an animal with sensorial knowledge. Where are these new beings coming from? Well, they're there in act to some degree, already in the matter in a hidden way. A proton and an electron in a field can act in potencies in various ways so that they can come together to make a new form, an atom. And in a similar way, we saw the hydrogen gas and the oxygen gas, when you put heat to them, that they will form water. So there's potency and actualities there that can be actuated. One actuality can act on the other's potency and vice versa. And there's new forms that can come about by those actualizations of different potentials among the inanimate things there. And this is sufficient explanation. In other words, we're saying it's in act, but it's in the act in a hidden way in the material things. And this is a sufficient explanation for organic chemistry and things right up to life. But something funny happens when you get to life. There's nothing in the inanimate material universe in act, and even in a remote way, like the nutritive actions of life. Life is heterogeneous parts ordered towards the eminent action of the whole. We don't see anything like that eminent action of the parts of the whole in the inanimate world. That's why we call it the inanimate world. So what causes this? If there's nothing in actuality in any remote way, it cannot be explained as being there already in a hidden way. So what causes the change? Well, the principle of causality says that nothing can change itself. Well, do we need to create new being? No. The universe, with all its potentiality, already exists. So matter already has the potential to become living matter because we're here after all. So we need a cause outside the universe? Not quite. Remember, the potency's there. We just need a general action of, for example, God, and we'll see it has to be God in the next chapter, that causes the putting in of this inanimate, this new form that is called for, in the same way we talked about the zygote, but this is a general action of God rather than a specific action of God that has to do only with life. When this potency of the matter is actualized in such a way that it's disposed to receive this form, the universe is created by God through what Jacques Maritain calls a superforming action of God, where he automatically brings this life form into being. Again, this order, the finality existed right from the beginning as part of creation. It's not an interference by God to do these things. An example would be if I were to take a bowling ball and roll it down the lane and it were to go sideways, that would be an interference of God. But that he acts his, if you can call it interference, which we'll see later, you can't call any action of God an interference, but from the standpoint of the universe itself, the impetus is given by God at the beginning. For him to withdraw that motion is for him to interfere with what he set himself to do. So if I throw the bowling ball, I expect it, and it will, barring a miracle, continue on its motion. And that, if God were to make it change, that would be the act of interference, not the act of continuing. In the same way, this causality exists in the potentiality of the universe at the very beginning, and God's superforming action is just carrying out that causality, that final causality that's already there. Each time there is a disposition for a new form, a new disposition, the general action of God causes that new form to come into existence. So every time we get a new ontological species, something like this happens. And then once this form is there, then all kinds of potentialities are open again, and they're open to the evolutionary process of change within that species by action of the environment on the species. At some point, the process brought, and again, I'm using species in the philosophical sense, not the biological. The species would, in a biological sense, would be a categorization, not a what is, but how do I find a way to put this so that sensible appearances are saved, so that sensible appearances are organized with fundamental first principles of the imperial schematic science. But I'm not saying that. I'm talking about the species, which is in an ontological sense, which is what the thing is. So at some point, so this process continues, and the environment works on these animals, brings each of the animals to some point where it's ready for the next, is disposed for the next stage, and the next stage comes. But at some point, we come to what I'll call an overdeveloped animal. And of course, for it to be matched to its environment, it cannot be overdeveloped in its own environment. It must be just overdeveloped with respect to the general environment. But by overdeveloped, I just mean that sensorial power has gotten so well developed, and not in the sense of having better senses, of having more finely tuned hearing or wider sight, but in the sense of being able to process that the advanced imaging ability and so on. You might want to use an analogy, a rough analogy. The microprocessor gets better. But what I really mean is that the higher power becomes more developed. And so we have that this animal can only live in a very narrow environment because its sensorial power is so developed that it's like a moped with a car motor on it. It's more of a detriment outside of its narrow environment than a help. And I call this man, and this again, we're trying to give a likely ontological explanation, something that explains the imperial metric, imperial schematic in a way that makes sense, but doesn't reject the results of the imperial schematic or the imperial metric. So there may be another way to explain this that is even better. What I give you here is an example of how you do it. So here I call this one penultimate man. He is called penultimate because the state of his sensorial knowledge is just short of a disposition calling for an intellect. As a purely sensorial creature, remember, he could do all kinds of things. He could start fires, so some of these analyses of cavemen and so forth are probably not men at all. They're this overdeveloped man that has this very advanced sensorial knowledge capabilities. Because remember, though, that this is only needing knowledge of particulars to do these kind of things. The understanding of what it is, what you're doing, is what comes with intellectual knowledge. So there's an infinite abyss still between penultimate man and man. Man is intellectual capacities that we just discussed. Penultimate man does not. There's an infinite jump. An infinite number of sensorial creatures does not equal one intellectual creature. The immaterial cannot be created out of the material. It's qualitatively different. We recall that a unique action of God is required for the creation of a man's substantial form. So at this point, when this man is just this penultimate man, not really a man at all, but penultimate in the sense right before man, he's at a transition point. Something is about to join the universe that's greater than the whole universe as it exists up to that point, the whole material universe. It is fitting then that there be a sharp transition. So I'll put a sharp transition in there. Again, this is here is an illustration to show you the limits of what you can say. You cannot say that a man just evolved out of an animal, because a man is qualitatively different than an animal. He has this ability of intellect, and thus has the immaterial substantial form. So two transitions must occur simultaneously. There must be a material transition that brings the disposition of the matter so that the sensorial knowledge is such that it can receive an intellectual soul, an intellectual substantial form. And then simultaneously when that happens, a direct creation of an infusion of the soul by God. So here's a possible scenario. To make it fitting, let's postulate, because remember, something infinitely larger than the current universe is about to enter the universe. Something that can comprehend the whole universe in its mind is about to enter the universe. To make it fitting, let's postulate that this penultimate man falls asleep. And while he's asleep, the activity of natural forces, which are geared to act in a certain way by God right from the very beginning, cosmic rays, whatever actions that are happening in the universe, and we're being pelted constantly by cosmic rays, and they're changing our DNA, and they're changing our appearance in slight ways. And this action could come to a focus, say, at this point, and the direct activity of God could refashion the sensorial knowledge in consonance with these actions of nature, and even alter his physical appearance in such a way that when this penultimate man wakes up, he's no longer penultimate man, but man. So we come back, we back up a little bit, and see, it doesn't seem like I've allowed anything room for chance in here. What is the role of chance? Empirological science, science of biology in particular, but also physics, uses chance a lot. It uses the beings of reason as its proper mode. In this, chance will appear in them as a means of explanation for three reasons. In its most proper sense, chance is a being of reason, by the way. And these are the three reasons that chance will appear in a theory. There's beings or mode of beings that cannot be properly represented in the empirological mode of explanation. And there are entities that can be incorporated, but have not yet been incorporated. So say you have as we gave in our example of an chip of iron falling, and it moved, and we noticed that there's a magnet there. So we then incorporated this magnetic field in there. Well, before we incorporated it, it could look like chance. Another example is if I flip a coin. I don't have a coin, so let me flip this matchbox. If I flip the matchbox moves in a certain way, and I can say heads or tails on the matchbox, and I'll say there's 50% chance that it's heads or tails. Well, there's all kinds of other causes acting on that matchbox, including the initial conditions that I set by hitting it, that are really there, but I didn't want to pay attention to them. I didn't want to incorporate them, so they appear as chance. So it appears that all there is 50% chance that the heads will appear and 50% tails. In fact, the thing is strictly causal. I've just chosen to leave out those entities for convenience of what I was interested in seeing. And the other reason is that there are causes outside the universe acting. For example, God acting would appear as chance. These three things appear in any given empiriological framework as imposed from the outside and thus appear irrational. Remember, the empiriological is trying to deal with the predictable and as such deals with the material causality. So in so doing, those things that are not material causality, that are not material, will appear as chance because they are outside the mode of explanation that you've allowed. In the case of mathematics, those things that are not consonant with mathematics will have to appear as an irrational element, or if you will, call it chance. Statistics is used also when you want to ignore something, as we just saw, like in the case of the penny. We didn't care the details. We just wanted to know what the probability that it's heads or tails is. So we need a working definition of chance. Indeed, I'm going to call it relative chance, because we'll see there's no such thing as absolute chance. Relative chance, or chance, is simply the intersection of two independent lines of causality. For example, a bird flying along and lightning coming down hitting the bird is the intersection of the bird's flight and this lightning. And there's an irrational element because the hitting seems to come from outside the system. For example, two pool balls, when given a certain velocity and starting position, will hit another pool ball. But if they're not within that range of velocities and positions, they will not hit it. And it looks like that this is a chance item until you back up and see that somebody is actually hitting it. Then you see it's not chance at all. But in the table plus ball system, there's an irrational element that you don't pay attention to, and that is the fact that you're hitting it. If you're a particularly bad player, then chance will be a more accurate description. It depends on, of course, how you look at it, how you analyze the system. But in the table plus ball system, the act of you is an irrational element. It appears as chance. There is no being in the system responsible, and thus it appears as without the being. Remember, we said the absence of being is irrationality, a lack of intelligibility. But absolute chance is complete irrationality. It's being coming from non-being. That's an impossibility. Something cannot come from nothing. That's basically a restatement of the principle of contradiction. Hence, those that think life is explained by chance are wrong, because chance is in a way of saying, I don't know what happened. Chance is a refusal to give an explanation. And we said in the case of the balls, initial conditions are specified. But they are, why are those initial conditions what they are? Usually you don't answer that question because you assume that you're leaving that part, you want to leave that part out, and you want to start from someplace. And also, not all conditions are possible, so there's already a limiting happening. And specifically, we noted that when we threw a rock, if we always throw it in the same way, it always acts in the same way. The potentiality is ordered towards act in a specific way. Every time you take hydrogen and oxygen and put heat to them, you'll get water, every time. Potentiality is ordered toward act. And once we say something is probable, we should note also, once we've said it's probable, then it exists in a potential way already. If the empiriometric laws are not geared such as to give life, including the initial conditions, there never would be life. So once we say something's probable, what we've already said is that it can happen, and therefore the potentiality is there. Evolution debates nearly, in the evolution debates, nearly everyone argues as if the issue is about the probability that life will occur. That is not the issue. They never seem to notice that probability assumes possibility. The universe is such that life can be. And this means that since the universe is such that life can be, this means that the universe is full of a profound type of being. Like all being, it is shot through with intelligibility, unity, and beauty. Intelligence is evidenced in all the beings of the universe. And this is what we said at the beginning. This intelligibility goes hand in hand with existence. It is on the back of the is of the universe that the chance gets its role. The relative chance, the what is not of relative chance, gets its existence, its being of reason existence. Chance, again, is a being of reason. Remember the coin flip. The coin flip depends on the coin being symmetrical, having two sides that are separated with an even thickness, and a certain environment and a certain way of flipping. If I were to flip it like this, it would not give the same probability. So there's the being is what determines what you leave out is what determines that there is relative chance. Again, relative chance cannot produce real being. Consider it's a case that people talk about all the time, and that is a monkey typing at a typewriter trying to type Shakespeare. People will say, well, if a monkey sat at a typewriter long enough, he'll eventually get Shakespeare. No, that's not true at all. He'll never get Shakespeare. I don't mean just in a long time, I mean never. On the other hand, a man standing over him, watching him, will eventually get Shakespeare. Because what's happening is the man has really found an awfully hard way of typing Shakespeare. And that is watch a monkey until he writes it. But the monkey didn't write it, the man wrote it. The man is the one that recognized that this is Shakespeare. In the end, chance events in the material universe must have their cause in God or angels or the like. There is no such thing as absolute chance. It would be being coming from non-being. And I want to bring this point home about the words. Remember, the words are instrumental signs. They are things who express an existence outside of the existence, this letter here has a given existence, and these set of letters have a given, but they're pointing to an existence beyond themselves. So even the typewriter itself is already part of the being on whose back chance sits. Because we have to have the man to see what the meaning of these things. The monkey can type out these letters that the man has put there in the typewriter, but he cannot recognize the meaning that they refer to. Only the man can do that. So we've seen the problems created by misinterpreting the empiriological as simply ontological. Irrationality can and often does invade the foundations of science by not recognizing this. We found how to understand by way of likely examples the ontology behind the empiriological. The key was not the specific examples themselves, but the need to do the work, to philosophically understand what the empiriological is telling you. We must keep first things first. We must remember what we know more certainly and move to what we know less certainly. Be careful not to start at the wrong place. And that always means that remembering that the imperial metric is about beings of reason that need to be, it's that hammer, it's a tool of physics that has to be looked at with the light of philosophy to understand what beings are causing the constellation of and beautiful patterns often that emerge in the making of these imperial metric and imperial schematic theories. But we also must remember that physics does not progress without these tools. These tools are our only means. In some cases, we might have to be content with these as being revealing what they can to us about these particular things. The short point is they need each other. One calls for the other. If you don't explicitly call for the philosophy after you've done the imperial metric. You'll graft your own philosophy on top of it. Typically, it will be a mechanistic philosophy that will exclude the things that really explain what you're seeing, and you will come up with all kinds of irrational conclusions. One of the ones we left out is the quantum mechanics, where they say that the world doesn't exist when you're not looking at it. They really say that. That's an imperiometric conclusion an ontological conclusion drawn from the imperial metric. And we saw that people even doubted the existence of the universe by promulgating this error. So in this chapter, we've assumed a lot about what God can do, talking about general actions of God, superforming actions of God, but we've not proved very much. And we don't want to lean on that. So we need to go back and prove some of this stuff. So in the next chapter, we're going to turn to him who we've glimpsed as truth himself. Metaphysics is the highest science. Studying him will reveal the principles of this highest science of metaphysics. And from there, we'll ask the question, what should we do? We'll move to the practical sciences and we'll ask, what should we do? And then we'll specify that question to our problem of the sciences. How then should we do science? And that'll be the last lecture.